Hello dear viewers, I'm Hawre Hosseini, a PhD student in computer science at the LS3 lab. I'm here to present my work with Dr. Ibrahim Bagheri with the title From Explicit to Implicit Entity Linking, a Learn to Rank Framework. So this is the outline of the talk. Alright, so according to very recent studies, sometimes Twitter users tend to tweet about things or people without mentioning a name explicitly. For instance, in a tweet such as, "Then there's Ethan Hawke and Patricia Arquette, easily the best characters and best performances of the movie." The Boyhood movie is the major topic of the tweet, while its name is not explicitly mentioned. In this example, you see a strong reference to the movie Boyhood, both semantically and through a textual placeholder. Here we can see the difference between explicit and implicit entities clearly. Compare Ethan Hawke with the movie, for example. According to literature, implicit mentions are very prevalent on Twitter. So what are we doing in this work? Our work's main motivation is that existing work on explicit entity linking have successfully adopted the learning to rank approach for identifying suitable entities. These approaches rely on a collection of features that link the content space to the entity space. We systematically categorize and present features for the context of implicit entity linking, though. Thereby, we design experiments for the sake of a comparative analysis of explicit and implicit linking, also improving implicit linking performance. Pereira et al. In 2016 introduced the notion of implicit entities in tweets, which will serve as one of the baselines for our experiments. They prepare and publicly share a dataset of tweets containing implicit entities in two domains, namely movies and books. In two works, in 2018 and 2019, we proposed an ad hoc retrieval approach in order to solve the problem. We also collected, manually labeled, and publicly shared a comprehensive dataset for this task. I'm going to talk about the dataset because we perform our experiments on it. Our dataset contains a two-level taxonomy with 6 coarse-grained classes or entity types, namely person, organization, location, product, event, and work. Pereira's dataset tweets are contained under work class. A total of 1,345 tweets with implicit mention is contained in this dataset. How do we do the linking? So it is done in 2 steps of candidate selection and candidate disambiguation. Formally, given a tweet and the type of the implicit entity that it contains, retrieve a set of entities relevant to tweet and of that type. This is candidate selection. But this step is followed by entity disambiguation, where the set of candidate entities is ranked, so target candidate entity is at rank 1. For the candidate selection phase, we adopt the method in Hosseini et al. 2019, but at candidate disambiguation, we view the tweet as a query in response to which entities should be ranked based on relevance. Candidate entities are represented by their textual content on Wikipedia. We categorize features in explicit entity linking literature, find out which of them are readily applicable to implicit entity linking. We adjust the ones that need adjustment. Also, tweaking some of such features will result in new features for implicit entity linking. Last but not least, we introduce some novel features. You can see the taxonomy of our features here. For description of each, please refer to the paper. But as an example, I just want to talk about clickstream, which is a novel feature we introduced. This feature captures the way users navigate on Wikipedia. It is extracted from the Wikipedia metadata and records how many times each linked entity on a specific entity's Wikipedia page has been clicked. This stream of clicks is hypothesized to show the different levels of relevance between an entity and other reachable entities. The feature takes explicit entities within the tweet and the target entity and calculates the click frequency between them. This is the experimental setup. Just 2 points for the sake of time. Explicit entity linking dataset that we use was provided by Mage et al. In 2012. It consists 318 tweets. As rankers, we use SVM rank models, and the specifications are as follows. We use linear kernel with 0.01 as the trade-off between training error and margin, and also as the loss function, we use the number of swap pairs summed over all inputs. First, it's important to mention that our focus was not to gain state-of-the-art performance for explicit linking. Hence, we performed explicit entity linking in a setup similar to implicit entity linking. This explains the poor results for explicit entity linking. However, this serves our purpose since we care about these results on a comparative basis. So we report the overall results for the implicit entity linking task and compare performance of the introduced features against two state-of-the-art baselines. As seen, the proposed features, when employed within the context of a learning track approach, show improved performance compared to the two baselines over all entity domains. To evaluate the importance of features, we draw upon their Gini scores. So we find that graph-based, something interesting about graph-based features. Literature on explicit entity linking report that graph-based features alone are enough for successfully performing linking. This point is reassured in our experiment as well. In case of implicit entity linking, however, only one of the graph-based features is to be found among the top 10. This shows the difference between the two tasks. We further perform experiments with different groups of features as categorized in our work. We run our systems with features of 4 groups, and we find these points. The first 3 points are for implicit entity linking majorly. So first, term-based features are the most discriminative features for performing implicit linking. With well-strung features, these term-based features are not as effective for explicit entity linking. Secondly, graph-based popularity features are quite effective for implicit linking. This can be in part due to the fact that users often use implicit mentions when they believe their audience can understand the implicit reference. Such identifiable entities are often those which have become hot in the social sphere or widely mentioned by the community. As such, graph-based popularity features that capture these characteristics are effective. On the other hand, these features are not useful for explicit linking at all. So the third point is that we find that popularity and network features have reinforcing effect on each other for implicit entity linking. And as such, it is helpful to include features from both categories when building an implicit entity linker. On the other hand, these features have an overlapping effect on each other for explicit linking, and inclusion of only network-based features seems to be a better strategy for explicit linking. So, on the contrary, graph-based network features are quite effective for explicit linking. Let's conclude this talk. So in this paper, we have adopted a learning to rank approach for performing the task of implicit entity linking. We have systematically categorized and introduced features that can be used for this purpose and compared their performance against the traditional explicit entity linking task. We report that the two tasks are different in nature and hence different types of features are appropriate for each. We further show feature importances for each feature as well as feature category. Through our experiments, we also demonstrate that it is possible to use the introduced features to outperform state-of-the-art. Thank you very much for watching this presentation and hope you stay safe. Also, feel free to follow me on Twitter with the handle Hawre Hosseini. Thanks again.